Welcome to the technical overview of Drop-02, an advanced automated plumbing and sanitary engineering design software. Please note that this is currently the beta version, representing our core computational engine. To begin the session, we will log in using our authenticated credentials to access the secure engineering workspace. The first interface is the Home and Project tab, which serves as the foundational data repository for your building's specifications. Here, we input the fundamental project information. Crucially, the number of floors parameter is globally auto-synchronized across the entire system. This single input establishes the total dynamic head baseline used in all subsequent hydraulic computations. As we define the floor count, the digital twin building section view on the right automatically adjusts. This digital twin is not merely an illustration. It is a spatial verification tool that helps us accurately visualize the vertical scale and hydraulic profile of the plumbing system in real time. Next is the Water Demand tab. Here, we define the baseline consumption metrics by selecting the specific type of building, occupancy, and inputting the estimated number of persons. By applying standard per capita consumption rates based on the chosen occupancy class, the software automatically computes the total average daily water demand. Establishing this precise daily demand is the critical first step, as it dictates the volumetric baseline required for all downstream storage and pumping calculations. In the Cistern and Overhead tab, we size the primary water storage structures, starting with the cistern tank. The daily water demand is auto-synced from the previous tab. We utilize two critical multipliers here: the percent demand to store, where 1.0 represents storing 100% of the daily demand, and the reserve duration, which factors in potential municipal supply interruptions, for instance, maintaining a 2-day reserve. Applying these yields the strict required capacity of the cistern. You then input your proposed cistern dimensions, length, width, and liquid depth, and the system automatically calculates the proposed volume. Once your proposed volume meets the required capacity, the status indicator turns green and displays adequate. The immense value here is parametric flexibility. If architectural floor plans change during an ongoing project and squeeze the available mechanical footprint, you can rapidly manipulate these spatial dimensions to ensure the volumetric demand is still mathematically satisfied without tedious manual recalculations. Moving to the overhead or roof tank sizing. The total daily demand is similarly displayed. Typically, roof tanks are sized to hold a fraction of the daily demand, often 1/3, 33%, to cover peak hour loads. This fractional reduction is critical to limit the massive hydrostatic debt load imposed on the building's structural apex, preventing excessive stress on the structural columns and beams, while still maintaining reliable gravity feed. While this fraction is adjustable based on specific engineering requirements, the primary objective is ensuring the proposed dimensions satisfy the resulting required capacity. The WSFU and DFU tab quantifies the specific hydraulic loads imposed by individual fixtures. First, for WSFU, water supply fixture units, you input the total quantity of each plumbing fixture. The software aggregates the total fixture units based on your selected engineering standard, whether that is the revised National Plumbing Code of the Philippines, RNPCP, the Uniform Plumbing Code, UPC, or the International Plumbing Code, IPC. It automatically distinguishes between private and public utilization, subsequently calculating the exact design flow in gallons per minute, GPM, for both flush tank and flush valve configurations. Similarly, for DFU, drainage fixture units, you input the total quantity of sanitary fixtures to establish the total DFU load. This absolute DFU value serves as the mathematical foundation for sizing the gravity drainage networks, ensuring that horizontal branches and vertical stacks can safely convey the anticipated wastewater flow. The cold water line CWL sizing and friction tab executes the core hydraulic pipe sizing. We again select our governing code, RNPC, PUPC, IPC, and our C factor. The C factor represents the internal pipe roughness based on material properties. For example, PVC versus galvanized iron. First, we select the system configuration. Domestic water pump upfeed utilizes direct mechanical pressurization to overcome static head. Transfer pump calculates flow for moving bulk water between storage tanks. And domestic water pump downfeed calculates gravity-driven systems, relying solely on elevation head. Our piping is structured in a strict parent-child tree hierarchy, main to distribution to header to fixture supply. This topology is critical because it mimics the actual branching of fluid mechanics, ensuring flow rates are correctly apportioned and proportionately reduced as water is distributed to individual zones. The software utilizes the Hazen-Williams formula to automatically calculate pipe sizing and continuous friction loss, expressed mathematically as friction head loss equals 10.67 multiplied by the pipe length multiplied by the flow rate divided by the C factor raised to the power of 1.852, all divided by the pipe diameter raised to the power of 4.87. This determines the precise energy loss to friction over the linear run of the pipe. The Drain, Waste, and Vent (DWV) sizing tab functions similarly to the CWL tab, but is governed by gravity flow dynamics and pneumatic pressure stabilization rather than pressurized flow. The Pump and Pressure Tank tab synthesizes our hydraulic data to specify the required mechanical equipment. It calculates the exact motor size required for your building. The engine processes several critical parameters: Q-flow in GPM, cut-in pressure, static head, calculated directly from the building height, total friction loss for pipes, total friction loss for fittings and valves, both seamlessly imported from the CWL tab, required residual pressure at the highest fixture, and overall pump efficiency. It also calculates the required hydropneumatic pressure tank sizing. The pressure tank provides a buffer volume of pressurized water to minimize short cycling of the booster pump motor, thereby extending equipment lifespan. Your system selection upfeed, transfer, or downfeed remains auto-synced here, ensuring the pump curve and total dynamic head calculations perfectly match the intended mechanical layout. The Pressure Zoning tab is a highly effective diagnostic tool for vertical hydraulic mapping. When designing a downfeed system utilizing a roof booster pump, this table displays the available static pressure at each individual floor level. If the static elevation head is insufficient to overcome pipe friction and provide adequate residual pressure at the highest floors, the system flags those levels with a needs pump warning. Levels with acceptable operating pressure are marked optimal. Conversely, if the cumulative hydrostatic pressure at the lower levels exceeds the maximum allowable threshold, the system automatically issues a warning that a pressure-reducing valve, PRV, is mandatory to prevent fixture blowout and pipe fatigue. We also have an add zone feature for booster and transfer pumps. While secondary to the main computation, this zoning capability greatly helps engineers visually partition the building project into manageable hydrostatic pressure zones. In the Septic and Storm tab, we handle decentralized environmental discharge and rainwater management. For septic sizing, the capacity is calculated based on the building population and the daily wastewater rate. A crucial regulatory compliance feature is integrated here. As per DENR Administrative Order, DAO 2016-8, and the Philippine Clean Water Act of 2004, if the calculated effluent volume exceeds the regulatory threshold, the system automatically triggers an error. Specifically, for volumes below 12 cubic meters, a standard RMPCP-compliant anaerobic septic vault is permitted for residential or small-scale commercial applications. However, for volumes above 12 to 15 cubic meters, a standard septic tank cannot consistently treat the organic load to meet strict DENR effluent parameters. Therefore, the system alerts you that a mechanized sewage treatment plant, STP, is legally mandatory. For storm drainage, you input the effective catchment area of the roof, the local maximum rainfall intensity, and the desired number of downspouts. The software processes these hydrological inputs to dictate the exact internal diameters required for both the vertical downspout leaders and the horizontal storm drains, ensuring the building envelope is protected against peak storm events without gutter overflow. The interceptor size and tab is dedicated to the precise separation of wastewater contaminants. Based on the specific commercial kitchen layout, you input actual DFUS for sinks, pre-rinse stations, or floor drains. For grease interceptors, it calculates total volume, partition thickness, and exact liquid depths for the 2/3 inlet and 1/3 outlet compartments for gravity and hydromechanical models. It also features dedicated auto-sizing for car wash and auto-repair waste interceptors based on floor area and vehicle turnover rates, ensuring hazardous hydrocarbons are stripped from the effluent before entering the municipal sewer. The Conversions tab is a real-time, multi-unit engineering calculator integrated directly into the workspace. It allows for immediate and precise translation across length, volume, pressure, flow, and power metrics, This eliminates the need for external reference when converting between metric units and imperial units, commonly intermixed in mechanical equipment datasheets and local material procurement. The Reference tab functions as an embedded digital library. It houses all critical tables, nomographs, and code excerpts directly from the RNPCP, UPC, and IPC. Having this codified data instantly accessible ensures that every engineering assumption made during the design process can be immediately verified against governing regulatory standards. The Recommendations tab operates as an automated engineering peer review. Based on the aggregated project geometry and calculated demands, the system generates intelligent design advisories. It provides standard operating configurations for your storage tanks, suggests the optimal pump type, such as an upfeed constant pressure system with a VFD for low-rise structures, and outputs governing principles for storm drainage and sewer operations to guide the engineer toward best practice design solutions. Finally, the report summary serves as the ultimate output compiler. It comprehensively aggregates all data generated throughout the system, summarizing water demands, calculated pipe sizing, exact pump specifications, and tank dimensions. This generates a definitive technical document that provides complete transparency and is immediately ready for drawing integration, municipal permitting, and project estimation. While Drop-02 revolutionizes plumbing and sanitary design, it is only the beginning. At HydroSync Engineering, our vision extends across all engineering disciplines. Today, we are proud to introduce our expanding ecosystem of automated design engines, built to synergize every facet of building construction. Introducing Ignis Pro, our fire protection design engine calculator. Operating with the same rigorous logic as Drop-02, Ignis Pro automates complex hydraulic network analysis for fire suppression systems. It processes density area curves, calculates continuous friction losses across intricate sprinkler grids and loops, and dictates precise fire pump sizing. Ignis Pro ensures absolute compliance with international fire codes, delivering life safety engineering with mathematical certainty. Next is Pulse, our comprehensive electrical design engine calculator. Pulse eliminates manual electrical tabulation by automating complex load scheduling and panel board balancing. The engine executes rigorous voltage drop calculations over extended cable runs and performs dynamic short-circuit analysis. By automatically sizing circuit breakers and wire gauges based on thermal and magnetic thresholds, Pulse guarantees a safe, optimized, and code-compliant electrical distribution network. For the structural framework, we developed TerraStruct. This advanced structural design engine calculator executes comprehensive load path analysis. By calculating dead, live, wind, and seismic loads against governing structural codes, TerraStruct automates the dimensional sizing of beams, columns, and slabs. It processes bending moments, shear forces, and calculates exact rebar detailing ratios, ensuring maximum structural integrity and material efficiency. To bring these designs to reality, we engineered Nexus Build, an AI-augmented construction project management platform. Moving beyond traditional scheduling, Nexus Build utilizes artificial intelligence to perform predictive risk analysis and critical path optimization. It automates resource leveling, generates instantaneous bills of quantities, and tracks real-time cost variances, empowering project managers with predictive data to eliminate costly construction delays. Looking ahead, HydroSync Engineering is actively developing the next major evolutionary leap: Automated Building Information Modeling, or BIM. We are moving beyond 2D calculations into parametric 3D spatial intelligence. Soon, by simply inputting baseline parameters like pipe sizes and flow rates, our engine will automatically generate fully routed CID MEPFS models. This update will feature automated fastening placement and real-time clash detection across mechanical, electrical, plumbing, fire, and structural disciplines, drastically reducing drafting time and eliminating spatial conflicts before construction even begins.